we should be thinking about the cohomology of Grassmannians. So the idea is that if alpha is in the cohomology of the infinite Grassmannian of n planes in R infinity, and I can also take the colimit over n, then sending E, a vector bundle to take the classifying map of E, pull back alpha, defines a characteristic class. So yeah, in a way, we've just reduced it to just studying the cohomology of these spaces. One important point is, or just one thing to emphasize, that this is a measure of vector bundles through cohomology, sort of as promised at the beginning. So this is a way to get there. So what we're going to do, I'm going to just give a brief, more of a summary treatment of Schubert cell, and also, while we're at it, variety structure for Grassmannians. So what we have to do is we have to fix a flag. So I've got the zero-dimensional vector space. There's only one of those, but then lots of one-dimensional vector spaces. So dimension of VI equals I. And the standard example, and that's pretty much the only example we'll be talking about today, but we might want to have multiple flags around. So that's one reason you introduce the others, is you consider the standard embedding of RK in Rn with zeros for the last n minus k coordinates. So so that's what a flag is. And then given some subspace, we consider, oh, and I think what I want to do is, this is an Rm. Maybe I'll even make this a m-dimensional. That will help to be consistent with my notes later. So we consider the collection, the ordered set of numbers, which are the dimensions of the intersection of W with VI. So this is a tuple of numbers, an M tuple. It's non-decreasing. And it increases at most by 1. So, so in other words, so increasing at most 1 in consecutive numbers differ by at most 1. The way to see that is just consider the projection onto VI modulo VI minus 1. That's one-dimensional, and the intersection either has image dimension 1 or dimension 0 there, and so little exact sequences show that the dimension before, dimension with the intersection of VI minus 1 and VI can jump by at most 1. So so what you can do is you can think of this as, what we have is let's emphasize, this is non-continuous sort of function or labeling on the Grassmannian. And what we'll call is SCH is the name I'll use for Schubert, that collection of numbers. So its values are in m-tuples of integers, or obviously subsets thereof because we're positive. Okay, and we're going to see that this is the different places where the this function is constant are going to be a lovely cell structure basically on the Grassmannian. Okay, but let's first develop some combinatorics, because we have these non-decreasing jump by at most one sequences. So I claim the following are equivalent, and just about all will be helpful. So first, I do have those dimensions. And so remember, the key is here that di minus 1 is equal to 0 or 1. Okay, so that's what we get by intersecting. If it jumps by 0 or 1 every time, I can just keep track of where it jumps by 0 or 1. The standard thing to do is keep track of where it jumps by 1. And so what we do is we've got collections. And of course, there's going to be exactly m jumps. So collections like this, and these are the places where it jumps. So what we say is just that sigma I is in this set sigma if and only if di minus 1 equals 1. So that's a translation between these two pieces of combinatorics. The other thing I could do is notice that these jumps, they can happen, they have to happen at least after sigma I has to be at least I. So what I can do is I can also and consider the n-tuples sigma 1 minus 1, sigma 2 minus 2. These are no longer in increasing order necessarily. But that gives us an n-tuple of numbers that that's pretty immediate to translate between this sigma and sigma prime. The other fun thing, and this is my favorite, is to consider lattice paths from, again, non-decreasing, so to speak, lattice paths from the origin to the point in the plane m minus n, comma n. So this is going to be less familiar, but a lot of fun. So again, these are very simple objects, but it's fun to look at the connections between them. I've got a nice lattice here. Let me go ahead and use that. So if this is my lattice, then every time I can move just to the right or up, let me make it one higher, I realize. be consistent with the example I had written before. So how does this work? Again, in terms of the way I read this is the dimension of intersection after in steps. So this is at most n, and this is m minus n. And the question is, where do I get up to dimension n? So in this path that I've drawn, I would have that d1 equals 0. There's no sigma 1 yet. Then I go up, and sigma 1 would be 2, and sigma 2 would be 3, because those are 2 jumps up. And then I would also have then that d2 is 1, and d3 is 2. And I'm going to the right, 2 moves, up, right, up. And so again, wherever d jumps, I go up, or equivalently, wherever I've got a sigma is a place that a step that I'm going up. So then what you can see from that is that, these are a standard object as well. And these correspond naturally to partitions of at most n constituent numbers each of which is less than m minus n. And by the way, I can switch the roles there, and obviously that would sort of correspond to a transposition. So how does that go? In this example, because I like to have the dimension going up with this, the partition that we're going to look at here is going to happen in the left. So in this example, I get the partition 1 plus 1 plus 3 plus 4. And this is basically the same as the as this list up here. Here what we have is, let me try to write it on here. We've got sigma 1 is 2. So 2 minus 1 is 1. Sigma 2 is 3, because the second and third places are where I'm going up. 4, I went to the right. 5, I went to the right. 6, I was going up. So sigma 3 is 6. And 7, I went to the right. In my 8th step, I went up. So sigma 8 equals 4. And if I take 2 minus 1, 3 minus 2, 6 minus 3, 8 minus 4, I get 1 plus 1 plus 3 plus 4. Okay. So these are all different ways to think about this same combinatorics. I enjoy combinatorics that arises in studying beautiful topological spaces like Rosmanians. And here's a great example. And so let's define a couple of these. You see it's natural to define the number, which I'm going to call absolute sigma, to be the sum of these numbers sigma I minus I. In other words, the number that is being partitioned. So in this case, that would be 9 in this little example, 1 plus 1 plus 3 plus 4. Great. So we're going to fix any way to think of this data, lattice paths, etc. We'll just all call it sigma, which is the second way, although the third, the sigma prime, is even more common perhaps, but we'll follow Milner and Sashef and use sigma to denote this data in the second sense. And then what we're going to do is define E sigma is going to be a subset of the Grassmannian to be, well, the subspace is W, so that the Schubert symbol of W is the given sigma. Okay? And the claims are that that E sigma is homomorphic, diffeomorphic, in fact, to an open cell of dimension given by this this value that we just defined, and that the well, so then what I can do is define a map from a closed cell to so then the map from the disk of this dimension to the closure of E sigma. First, it does extend from the open disk to the closed disk. I think that just follows by compactness. And then this defines a CW structure. So that is that the images of boundaries go to cells of lower dimension. And let me add something else. So, or let me just sort of a third claim that these closures E, or this is more of a remark. These are called Schubert varieties, which we'll see, which have singularities but have what I think of but with canonical, or at least straightforward, I'll say, with some pretty standard ways you'll want to resolve those singularities. So a simple example, in the CW decompositions of tori or projective spaces, which by the way are a special case. Of course, if I'm looking at n=1, the lines in a vector space, that's a projective space. There, the closures of the cells are themselves smooth objects, but that's quite special. What happens more in nature is that you've got some things with singularities, and we'll see those. I want to just go through this. So this is, again, from chapter 6 in Milner and Stasheff. I want to go through this in an example. Very carefully, and then what we'll do is just talk about the general case and mostly just refer you to Milner and Stasheff's treatments. There's plenty of good treatments out there of these. My colleague Boris Botvinnik has a nice write-up, pretty complete. But this is also, again, Milner and Stasheff. So I'm going to do the example when, oh, one other thing to say here, because it's pretty clear from any one of these, the second one especially, I'm choosing in things out of a list of M. So there's M choose N of these Schubert symbols. So let me maybe say that over here. this implies there are im choose in such, regardless of how we look at it. You're choosing where you jump. Okay. So the example again is we want to look at GR2, R4. That's the first case. It's not a projective space. We're going to use a standard flag, R0 and R1 and R2 and R3 and R4. Then let me use the lattice paths. Let's see, if we go down here, yep, I think that should be enough room. So we've got 2 by 4 minus 2. And the first thing, let me maybe use blue, is this lattice path where there's nothing to the left. Let's read it off in terms of dimension. D1 is 1, D2 is 1. The only way D1 can be 1 is if the subspace contains R1, but especially the only way D2 can be 2 is if you are just the R2 itself sitting inside R4. So W equals R2 here. We're gonna elaborate more in a bit. Let's go ahead and just list all the possibilities. The next thing, well, there's only one in one dimension. Goes like this. Again, we have one block, which is to the right, or sorry, to the left and above the path. In the next, there's going to be 2. And those can be fairly different. One is to go up again, go over twice. The other is to go over and then up. And then the 2 more cells, there's 4 choose 2, which is 6 cells. The last one is when W is quote unquote generic, doesn't really intersect any of these flags in a standard way. Of course, it's got to intersect R3 in dimension 1, and it's got to intersect R4 in dimension 2 because it sits inside R4. But nothing happens before that. Whereas here we finally have that. And again, if we want, we can sort of shade in above and to the left, and you get the dimensions involved. I'll go ahead and just write them. Dimension 4, so the this Grossmanian is 4-dimensional, and that's the sort of the top dimensional cell, as we'll see, 3, 2, 1, 0. Okay, so at the bottom we have W equals R2, and that really is just a point then, so that's good, that's a 0 cell. So the space. So if I've got my symbols, and again, I'll call these pictures sigmas as well. So let X sub sigma be, so again, we have E sub sigma is the corresponding cell. Let's let X sub sigma be the closure of E sigma. And in some cases, we'll have an X sigma hat as a blowup. So then in this case, for this sigma, X sub sigma is a point. that's also E of sigma. Next, okay, so let's read off through this path what that means about the W. Next, that means that W, well, it's got to contain R1, and then it also makes it up to the top in the third step. So R1 is contained inside of W is contained in R3. Well, since I know it contains R1, I could quotient, for example. So take the quotient by R1 of this, and I get a line in R2. And we see that this is a copy of P1. The cell would just be, P1 is of course S1. The cell is the interior, it's the interior of the interval before you take the quotient of the two endpoints to make S1. So, and this is really, you go back and forth. If I have an L and R2, then I can make a W that contains R1 and sits in R3 once I say pick how I want to, which coordinate is being projected off or something like that. Which is again, that's not even a choice. It's the first coordinate here. So we see here this X sigma is an RP1, and again contains the first X sub sigma as just sort of the special point, the point at infinity in RP1. Okay, it gets more fun next time. There's actually two possibilities, so we'll kind of divide things and talk about them both to the right here. So next, we want to think about, well, it's a similar story. You contain, because that first step is one-dimensional. That means that once again, W contains R1. Of course, that's got to be proper, by the way, if I want. And both of these have to be proper. But now it sits inside of R4. And once again, I can play the same game, and I'm seeing, and this is maybe sounding boring, oh, that's just RP2 for this particular X sigma. What's a lot more fun is to go over to the right. So generically, what this says is that, I'm not going to contain R1, but the first interesting thing that happens, that first jump up, because again, generically, I just move to the right or move up. That first jump up says that the dimension of W intersected with R2 is 1. So I have a line. So generically, in the interior of the cell, W intersect R2 is an L1. And then what you can do is you could say, again, generically, just quotient by that R2, and you've got something in an R2, R4 mod R2, or an R2, and you look at the quotient, you get an L2 inside of R4 mod R2, which is R2. So this somehow looks like RP1 cross RP1. And again, E sigma is naturally an open interval cross an open interval. So you really just get a product, but X sigma is going to be more interesting. And the way to see that is actually to first blow up. So let's by considering, instead of just the W in R4 that satisfy these, that have this for its Schubert cell, or are in the closure. So again, what's easier is to show that the interior is a cell. What's harder is to do the fun analysis of what does the closure look like. So we consider the W inside of R4 such that the dimension of W intersect R2 is at least 1. And then what we're going to do is not just have that W, so that will be, this is somehow in the closure, right? We're including, for example, that the first base point when you just, and that's a key example. That's where the blow up is really going to happen. So along with an L, or maybe call it L1, inside W intersect R2. So generically, for all but one W, namely R2 itself, that there's just going to be one choice of L. But when W is R2, I've blown up, and this thing fibers over RP1 by sending such pairs W and L1 to L1. And then the fiber, if I pick an L1, then I'm going to look at completing the W, and so I get a line in L perp, but that's got to happen within 3 steps, right? So that's a 2-dimensional line. So we see that this thing, which wasn't our, that's more than our closure, fibers over RP1, which is a circle. The fiber is also RP1, which is a circle. There's 2 different ways that we can have a nice fibering of a circle over a circle, especially there's only 2 smooth. And I don't want to think about what could maybe go wrong in general, but and those would be the torus and the Klein bottle. And the claim is that this is a Klein bottle. So this is a Klein bottle. You convince yourself of that by taking the point, the L1 in the plane that I've intersected with, and letting it turn to itself again. So that's a loop in the base. And what happens is that the L perp goes through an orientation reversing. The lines in L perp go through an orientation reversing homeomorphism. And this Klein bottle is then what I'll call X sigma hat. It's a smooth resolution. And then the X sigma is a Klein bottle modulo an RP1 inside there is getting identified with shrunk to a point. Because again, for that special W, which corresponded, it's always happening in the lower dimensional strata, so to speak. The special W, which was just R2 itself, we had to, in this blow-up construction, we have a whole P1's worth of points there, where in X sigma, there's no choice of line. Generically in X sigma, there's a unique choice of line over over that special point where W is R2 itself. We have an RP1 above. So running that backwards, if our X sigma hat is a Klein bottle, then our X sigma is what's obtained from a Klein bottle by taking that RP1 and squishing it to a point. So that's some fun and games there. Sort of beyond what's in Milner and Stasheff and most treatments, but I don't know. I don't want to leave all that kind of fun to the algebraic geometers. There's going to be a similar thing we can do here. I'm going to leave these for exercises. Of course, this one is the Grassmannian itself. And a lot of Schubert varieties are just Grassmannians inside of Grassmannians. That's not, shouldn't be surprising. We saw RP1 inside there. And this, I'll just say exercise, run through the structure here. It's, yeah, this shouldn't be a difficult exercise in light of what just happened. Another exercise is to repeat this whole thing for, say, GR2, R5. If you do that, you'll really understand not just the cell structure, but just the geometry of the closures is a beautiful story itself. Let's talk about the cell structure, though. Let's get back to that. And again, I'm going to just sort of sketch things. First, let's define HK open to be the subset of RK, which again is often sitting inside RM, so that the last non-zero coordinate is positive. Then HK is has last coordinate non-negative, the closure of HK open. Let's see. And then let's make some claims. Again, I'm just giving a highlight of what you need to check at this point to get the result that we've got a CW structure here. First, something has Schubert symbol sigma if and only if W has a special kind of basis for which, let me call that B1 through Bn, because it's n-dimensional, so that Bi is in the open half space. So that's pretty immediate. I don't think I want to say more about that. That's a claim that you can, now that we've seen the examples above, you can run it through in examples above as an exercise for the various sigma that I listed for the Grassmannian of two planes in R4. And then standard choosing orthonormal says that that will happen if and only if W has an orthonormal basis and then the fact is that which is unique. That's lemma 6.2 in Milner and Stasheff. So how does this go? Let's take the top cell. By the way, yeah. So we didn't look at that one as far as looking at X sigma. I left that to you. But let's now think about the interior of the top cell. So I'm thinking about this sigma or this path. And what happens? So in my second step, I contain our in my second step, I've got a one-dimensional intersection. So that means that I contain some line. So we can say that the Schubert symbol of W equals sigma means that W contains some L1, and now I'm in the interior of the cell. So the way I want to draw this I've got my standard flag, which is my R2. Then the half space is over here where the Y coordinate is positive. So, and my L1 is contained in that half space. There's a basis where my first basis vector is going to be in this half space. So if I draw my L1, it's like this. And then if I look for orthonormal, that just means looking for a unit vector. And so the cell itself, there's a one cell's worth of first basis vectors. An open one cell parametrizing the first basis vector. And then, and my drawing is going to get a little bit not as good, but in fact, let me say it over here. What I do is, well, I'll redraw just the line. So I have this line, and what I do is I consider L perp okay, that's going to be three-dimensional. And the second basis vector is going to sit there. Maybe I'll try to draw L perp like this. If that's my L perp, there's going to be the intersection of this with things that have the positive half space, and this is sort of infinite anyway. And so what you so within that L perp, I've got a I can first of all think of the unit sphere, and that's an S2. But then once I take the positive things, and I'll sort of draw it like this. Once I take the positive things in there, that means that I'm only looking at half of that S2. And in fact, not the equator either, because this is the open cell. So then I've got an interior of an open 2 cells worth of possibilities for the second basis vector. And that's basically it. Then this becomes an interesting kind of fibering when you close things up. Well, in order to have a fibering, you have to blow up, as I did before. But in this case, all we need is for these open cells. We can identify this fibering with actually a product structure. So, so yeah, let me just give you the guide to what Milner and Stasheff do from here, and sort of let folks read there if they want to understand the details better. So then the key definition, so we're going to let E prime sigma is going to be the space of orthonormal frames so that, oops, let's see. Sorry, let me move this over. So E prime sigma is sitting in a different space. It's sitting inside the in frames within RK, and it's the subspace of orthonormal frames so that B1 dot 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 Bn, so that Bi is in this open half space. Okay, and then E prime sigma. So that's sitting up in the frames, not the Grassmannian. The frame sits over the Grassmannian because I can take the span of a frame, and if I close it up, then all I'm caring about is that Bi is in H sigma I without the, so now I've closed it up, and then inside this frame space, this is lemma 6.3, and then we're going to talk about theorem 6.4. Inside the frame space, E prime sigma is a closed ball of dimension, the standard kind of degree of sigma. And then if we let Q be the map from in frames in Rm to the Grassmannian, then right, it sends and which sends E prime sigma, sorry. And, sorry, Q sends E prime of sigma to E of sigma. So it sends that open cell homeomorphically onto its this open cell in the Grassmannian, and then Q sends the boundary, and this is basically all that's left to prove in theorem 6.4, telling us that we've got a CW structure that Q sends the boundary of this cell to cells of lower dimension. There's plenty of work. I'm not going to go through all of it, but I think I've outlined it pretty well. At this point, I think it's just a bit of quiet study. If you want to understand the details, I would, of course, recommend going through what this looks like in our example of GR2 R4. We've got plenty of sigmas to look at here, plenty of cases of open cells. Again, it is kind of remarkable in light of the fact that the closures are not products. They're twisted products. You maybe have a quotient blowdown of a twisted product is, but on the interior, you know, if you think about the Klein bottle with a circle fiber collapsed, you still have a perfectly good interior of a 2-cell on that has a CW structure, and that's fine. So this is to give you an idea of the amount of singularity, even though things are really beautiful as they need to be within the cells. So I think I'll stop there.